Hello everyone and welcome to this next class. So last lesson we dealt with digital electronics, a bit of an introduction to it, which was looking at different number systems. So just to recap, we learnt about 4 different number systems: decimal, binary, octal and hexadecimal. We looked at, went from the very basics, which was how to count in decimal, which I'm sure you all knew how to do, but I just wanted to start with decimal so you can get down the fundamentals of how we were going to count with octal, hexadecimal and in binary. So if you don't know how to do any of that, if you don't know what binary is all about, if you don't know what octal is all about or hexadecimal, if you don't know how to convert from binary to decimal, hexadecimal or octal, then I suggest that you click, let's say here, actually, I'll be fancy. Click here to go and watch that now. Okay. Alright, so this one is a continuation from the previous one. We're still looking at number systems, but now we're going to look at where we can actually use these, and we're also going to look at how we can convert between each other. So last time we just did binary to decimal, binary to octal, binary to hexadecimal. So now we're going to start looking at going from hexadecimal perhaps to decimal, or hexadecimal to binary, or something like that. So let's check this one out. Let's start off with the decimal number. Actually no, let's start off with binary, because this is something we've done before. So we'll start off with the binary, and let's make it, I don't know, 6 digits. 10101. That seems pretty good. So we're going to convert this first to decimal, then we'll convert it to octal, then we'll convert it to hexadecimal. Then we'll see about converting it back, and hopefully we should get the same result. Okay, so first let's do binary to decimal. So we're going to use this number, 10101. To convert it to decimal, you'll recall that we need to figure out the weighting of each one of these columns. So starting at the right hand column, that is worth the least, and as we keep stepping across, each column is worth more. So we get 1, 2, 4, 8, 16. Now if you've forgotten what all of these numbers are about, again, go back to the previous one and check it out, because I describe where we get all these weightings from. So check that out if you need to. So we've got one of these, so we've got 16, plus we've got none of them, we've got one of the 4s, so we'll do plus 4, we've got none of the 2s, and we've got one of the 1s. So in this case, it's 16 plus 4 plus 1, and I don't have my calculator, but I think that's 21. So there we go, 10101 equals 21 in decimal. So let's write that up. 21. Okay, let's go binary to octal. That sounds like fun. Some of my markers are a bit squeaky, but hopefully that's alright. What are we doing? Binary to octal. So you may recall that any 3 binary digits make up one octal digit. If you're not sure about that, go back to the previous tutorial or lesson and check that out again, because I describe it all in that one. So same number, 10101. That's what I was trying to say. And starting from the right, we break it up into 3s. 1, 2, 3. And again, you'll notice that there's not 3 digits here. You'll recall from last time, we just chuck in an extra 0. That doesn't change the number at all, but it does give us a block of 3 to work with. Now we treat these as individual blocks, so we're going to get 1, 2, 4, 1, 2, 4. And of course, if we had more binary digits, it'd be again split up into 3, 1, 2, 4, split up into 3, 1, 2, 4. They're just separate elements. So this one looks pretty easy. We've got no 4s, we've got 1, 2, we've got no 1s, so that's just 2. This one, we've got 1, 4, we've got no 2s, we've got 1, 1, so that's 5. So that same number is 2, 5 in octal. So let's write that up here. And let's do our last number system, which is hexadecimal. Let's do green, that's a nice colour. So, starting with binary again, we're doing binary to hex, a decimal. Write up the number. You may recall from the last one that we break this up into groups of 4, because any block of 4 binary numbers will work out to be just one hexadecimal number or digit. So starting from the right, we go 1, 2, 3, 4, split it up, and then I just need to throw in a whole heap of zeros here to give it another block of 4. Then you may recall that we put above here 1, 2, 4, 8, 1, 2, 4, 8, and just as with octal, if we had more digits, we'd split it up into 4, and we go 1, 2, 4, 8, split it up into 4, 1, 2, 4, 8. They're each their own block, consisting of 4 bits. This one here, very simple. We've got no 8s, we've got no 4s, no 2s, we've got 1, 1, so that's simply just a 1. Over here, we've got no 8s, we've got 1, 4, we've got no 2s, we've got 1, 1, so that becomes 5. So that is 1, 5 hexadecimal. So all of these right here, they actually represent exactly the same amount of something. So if we remember back to my previous tutorial, I was talking about driving in a car. So let's start with decimal. If we're driving in the car, and let's say we drove 21 kilometres, I'm from Australia, I deal with kilometres, 21 kilometres, I would have driven, a distance of 21 kilometres. If I then came along and jumped in my octal car, and I drove exactly the same distance, on my octal odometer, it would display the numbers 25, but I've driven the same distance. If I jump in my hexadecimal car and I drive exactly the same distance and park next to these two cars, on my odometer in my hexadecimal car would be 15. Exactly the same distance, it's just a different number because I'm using a different number system. Jump in our binary car, I drive exactly the same distance as the previous 3. On my odometer would display 10101. So it's just different ways of representing exactly the same amount of something. So how could this be used? A good example is, let's say we had a little 8x8 LED matrix. Let me grab one. So here's one right here, little 8x8 LED matrix. Very cool. I love using LEDs because you can make pretty things happen. So here's an 8x8 LED matrix. I'll draw this up on the board for you all. So let's say, for instance, we wanted to draw a smiley face on this matrix. Well, it might look something like this. There we go. There you go. Hopefully that looks like a smiley face from where you're seeing it. So 8 pixels by 8 pixels gives us 64 pixels in all. And something that's pretty cool to do with one of these is display a smiley face. So there's one right there. So if we were to break this up into blocks of 8 bits of binary information, what we would need to do is send out to this display 8 blocks of 8 bits. So for this first one, a 0 would represent the LED being turned off, and a 1 would represent it being turned on. So if we break this up into 8 blocks of 8 bits, what we would need to send out is the binary 00111100. That takes care of the top row. And then we keep coming down and we go 0, 1, 0, 0, 0, 0, 1, 0. So I'll just keep doing this down here. Like that. And there. That one. And last of all, so perhaps in there you can see the smiley face again, but made up with a whole heap of binary ones and zeros. So this is a good application or a good example of where it's really cool to use binary digits. Because with binary, we can actually see, in this case, what LEDs will be turned on and what LEDs will be turned off. So we can actually see the picture in the binary. But it gets a little bit annoying to have to write up all of these digits. So, I mean, there's 64 digits there, so I've got to be typing them into my keyboard in order to program this little smiley face onto the display. What you can do instead is you can send out the same information to the display, but use something like octal or perhaps hexadecimal. We'll use hexadecimal and we'll see why that is a lot better to use. So we'll start with the top row, I guess. Actually, we'll just do them all. So I can split this into groups of 4. So 1, 2, 3, 4, and then over this side 1, 2, 3, 4. And I guess I can split it up this way as well. Just like that. And if you remember, any group of 4 binary digits becomes one hexadecimal digit. So here's my 1, 2, 4, 8, 1, 2, 4, 8. And so I'll start with these rows over here, and then I'll go over to these ones over here. So starting at the top, I've got 8 and 4, and no 2s and no 1s. So basically I've got 8 plus 4, and if you're not sure how to do this, again, go back to the previous tutorial, because you will find out right there. So we've got 8, and we're going to add 4, so 8, 9, A, B, C, so that becomes C. Now we're going to go to this next line. We've got no 8s, no 4s, 1, 2, no 1, so that just becomes 2. Here we've got 4 and 1, so that becomes 5. That just becomes 1. We've got a 4 and a 1, so that becomes 5. We've got an 8 and a 1, that becomes 9. And here we've just got a 2. That becomes 2, and the last one is just the same as the top, so it's C again. Coming over the right hand side, we've got a 2 and a 1, so that's a 3. We've got just a 4, so that's a 4. 8 and a 2, so it's 8, 9A. So remember, it's hexadecimal here. Just 8 for that one. We've got an 8 and a 2, so again that is A. Here we've got an 8 and a 1, so that is 9. Here's a 4. And for the last one down here, we've got a 2 and a 1, so that is 3. So we can compress all of that down to this. 3C, 4-2, A5, 8-1, A5, 9942, and finally we finish it off with 3C again. So, my little LED matrix display, if I was programming this with like a little microcontroller chip, if I wanted to display a smiley face on this screen, I could either type out all these ones and zeros, send it to the display, it would display a smiley face. What I could also do is I could just type it out in hexadecimal like this. You can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 digits as opposed to 64. Send it out to the screen, it would display the same thing because these are the same numbers. Mean exactly the same thing. So perhaps that's a pretty cool thing. What about another use of where we might want to use a different number system? Well, how about, so we'll talk about this a bit later, but I'll bring it up now. Address buses in a computer. So any of you who have dealt with address buses before, you may have been dealing with like hexadecimal addresses. For example, if we have a 32-bit address bus on our computer, then each individual address is a different location on the computer. So it could be an address in your memory, so your RAM, it could be an address in the ROM, it could be talking to the hard drive, it could be talking to the DVD drive, the printer, all these different addresses. So let's say we've got one specific address. There is a 32 bits. So there's a 32-bit combination on our address bus. So let's say that you're a technician working on some kind of computer system and you needed to have a look at what data was located at this address here. So it's a little bit annoying having to look up a manual and go, okay, what address am I looking for? And so I'm looking for 10110010, and so it's just too annoying to read. What we can instead do is have this manual that he's looking at, and instead of having to figure out a big 32-bit binary address, the manual would most probably have this converted into hexadecimal. So it would be broken up into 4s. That worked out well. And we treat these as individual blocks. So 1, 2, 4, 8 above all of these. So I won't go right through, but just imagine 1, 2, 4, 8 for each of them. So this first one would be 8 plus 2 plus 1, which would be B. So 8, 9A, B. This one is just 2. This one again is B. This one is 2. This is 2. That is F. This one is 2. I didn't realize there'd be so many 2s. And this last one is going to be D. So 8 plus 4 gives us 8. 9, A, B, C, plus another 1 puts us at D. So in the manual this technician's looking at, he is now just looking for the address B2, B2 to F2D, and he would then have a look at the data that is contained at that address, and then he could go on with his troubleshooting. So we've compressed 32 binary digits down to 1, 2, 3, 4, 5, 6, 7, 8 hexadecimal digits. A lot easier to read, a lot easier to work with if you have to type it into a keyboard. And I think I've said everything I need to there. So hopefully you're starting to see why it's pretty cool to have a few different number systems. Binary, it's very good if we're talking about the state of LEDs. If we're typing in binary, we can say, okay, there's a logic 1, that LED should be on. There's a logic 0, it should be off. But instead of having to type out all of these digits, if we instead code it in something like hexadecimal, which is most often used, you can see we can compress that same information right down to just a few digits. Alright, well what about your calculator? So I don't actually have one on me, but I do have an iPhone. So here's one right here. So with a calculator. So if I wanted to add some things up, let's have a look at this. If I wanted to do 2 plus 6, let's say, it's giving me the answer as a decimal, which is really cool. The internal workings of your calculator, however, uses binary. So what the calculator could do, it could just give us 2 buttons on there. 1 and 0. If we wanted to calculate whatever number, add or subtract, divide, whatever, we could do it with this calculator, but I'm guessing the screen would have to be something like this big. So we'd have our 1 and our 0, and then we'd have our add, divide, subtract, multiply, we'd have equals. Probably could have drawn that better, but oh well. So we would have to add these numbers together. So if I did 2 plus 6, I would first have to convert them in my head to binary, add them or subtract them, whatever I wanted to do. In this case it was add. And then this would give me the answer in binary, which is really annoying because I'd rather just work with decimal. So what happens within the calculator is it gives us a nice keypad with actual 1, 2, 3, 4, 5, 6, 7, 8, 9. That's not going to work out. There we go. Let's just pretend that that's good. So it gives us a nice decimal keypad. So we enter the numbers in decimal. It then converts from decimal into binary because all the internal workings of your computer is done in binary. It will then figure out the answer and then convert it back to decimal so it can display it on the screen in decimal. So what I'm getting at here is we use decimal in the real world. So we were all born with 10 fingers and we were created to live in an ordered world. The whole world is very ordered. So our 10 fingers line up perfectly with the decimal number system. So that's what we use every day. However, computers and calculators love to work with binary because it's just so easy to turn a transistor on or off. So we can put our numbers in decimal. We want the answer in decimal, but the calculator will take care of the conversion to and from binary for us. So, much better than trying to use a binary calculator and then convert it all yourself. So number systems, very, very handy indeed. Alright, so we've got these ones. Binary, decimal, octal, hexadecimal. We first started with binary and we figured out that 10101 is exactly the same number as 21 decimal, is exactly the same as 25 octal, is exactly the same as 15 hexadecimal. So how about now we look at converting, let's say, from decimal to, actually let's go back to binary and see if this actually does come back to that. So what we need to do for this, I'll just put this down over here. We actually need to use what I like to call the divide by system. Anytime we're going from decimal to binary, octal or hexadecimal, any of these other number systems, we always divide by the base number that we're going to. So in this example, decimal to binary, we will be dividing by 2 because the base of binary is 2. If you're unsure of that, go back to the last video. And the answer, what we're looking for with the answer is a whole number and either a remainder of 0, which means that it went into it perfectly, or we get a remainder of 1. That's all we can get if we're dividing by 2. The answer is actually in the remainders. So this is what we do. We start with 21, divide by 2. We're going to get some number and a remainder. And we keep doing this until we end up with 0. So let's have a look at this. 21 divided by 2. We're getting 10.5. So we put the whole number down and then we write down the remainder. So the remainder is whatever is after the decimal point. So let's figure that out. Take away the 10 and we're left with what's after the decimal point. And and it's 0.5 of 2. So we multiply it by 2 to figure out what 0.5 of 2 is. Pretty easy, it's 1. So what just happened there was we did 21 divided by 2. So the number 2 went into 21 10 full times. So if we had 10 of these 2's, they fit perfectly into 21. But then there's this little tiny gap where we need to fill in the 1. And in order to fill that gap, we need half of one of these. So that's where we get the remainder 1 from. So 2 goes into that 10 times, and then we've got 1 left over. Now we use this 10 and divide by 2. So that should be nice and easy. Let's go 10 divided by 2, and we get the nice round number 5. Sort of round. So obviously it's going to have a remainder of 0 because 2 went into 10 5 times, remainder 0. And we just keep going until we get 0 on this side. 5 divided by 2, so I'm going to divide that by 2. And we get 2.5, so we're going to get 2 remainder, and if you remember, 0.5 of 2 is just 1. 2 divided by 2, that should be pretty easy. So 2 divided by 2 is 1. And because it went into it perfectly, we had a remainder of 0. 1 divided by 2, I'm running out of space down here. 1 divided by 2 is 0, remainder 0.5, and remember 0.5 of 2 is 1. And then of course 0 divided by 2 is just 0. So we could just keep going if we wanted to and just keep adding zeros all the way down, but there's no point in that. We actually read the answer from the bottom to the top and we write it out like that. So 21 in decimal equals 10101 in binary. So maybe I should have gone with a different number because reading from top to the bottom, it's exactly the same thing. But yeah, anytime we do this, we start with the decimal number, we divide by 2 because we're going to binary, and we keep doing that until we get down to 0. Alright, so let's now go on with octal and see if we can convert from decimal to octal. 21 in decimal should equal 25 there. We've just discovered that 21 decimal using this system does actually come to 10101 in binary. Alright, so I just said to you before that in order to get to from decimal to any other number system, we just use the divide by method. That's what I call it. I don't know who came up with it. It might be called something else, but that's how I refer to it. So again, 21 divided by the base number of what we're going to, which is octal. So it's a base number of 8. We're going to get some number and remainder 0, 1, 2, 3, 4, 5, 6 or 7, which lines up with all the numbers that we get in the octal number system. So let's do this on the calculator. 21 divided by 8, and we're getting 2.625. So we write down the whole number, 2, and then its remainder 0.625, or its remainder 0.625 of 8. So in order to figure out what that is, we take away the 2, which leaves us with the numbers past the decimal place. So what is 0.625 of 8? Well, we just multiply it by 8 and find out that it's 5. So it's 2, remainder 5. We keep dividing by 8 until we get to 0. 2 divided by 8, let's do that on the calculator. 2 divided by 8, we get 0, so write that down so we don't need to go any further. And then we've got 0.25 left over, which is 0.25 of the 8. So we multiply that by 8 to figure out how much that is, and it's 2. So it's 0, remainder 2. Just as we did for binary, we worked out the answer was read from the bottom to the top. So starting from the bottom, we get 2 and then 5 working our way to the top, which is 25 in octal. So there's that one. Let's move on to hexadecimal, which is our last one. So we're dealing with 21 decimal. We're going to hexadecimal. Anytime we're going from decimal to hex, we use the divide by method. So 21 divided by the base number, which is 16. So let's figure this out. 21 divided by 16. And we get 1, so 16 goes into there 1 full time, and then remainder 0.3125 of 16. So let's figure out what that is. So 0.3125 of 16 is 5. So it's 1, remainder 5. And we keep going until we get to 0 on this side. 1 divided by 16, well 16 goes into it no times at all. And then we're going to get a remainder of, so let's have a look, 1 divided by 16. So none, remainder 0.0625 of 16. So how much is that? That's 1. So we get a remainder of 1. No point in going any further, because we're just going to keep ending up with zeros, which doesn't change the number. As for the last two, we read from bottom to top, and the answer is 15 hexadecimal. Alright, very handy. So in the last two videos, this one and the last one, we've learnt how to go from binary to any of the other number systems. In this video, we've learnt how to go from decimal to binary, to octal to hexadecimal. How about we do octal and then hexadecimal to binary? Let's do octal to decimal and see how that works out. So we start off with the octal number 25, or 25 I should say, sorry, not 25. 25. Just as we did from binary to decimal, we needed to figure out the weighting of each of these columns or digits. In order to do that, and I'll just move this down. In order to do that, we put the base number above each digit. Since it's octal, it's a base of 8. And then we put another base of 8 above there. Starting from the right, we raise it to the power of 0. And then we move across, raise it to the power of 1. If we had more digits, raise it to the power of 2, then 3, and so on. 8 to the power of 0 just gives us 1. 8 to the power of 1 gives us 8. The next one, 8 to the power of 2, which would be 8 times 8, gives us 64. Then it goes to 5, 12, and it just keeps going up by a factor of 8. Oops. So in this example, what we've got is 2 of the 8s and 5 of the 1s. 2 times 8 is 16. And then we've got 5 of the 1s, which is just 5. 16 plus 5 equals 21. Yes, very good. How about octal back to binary? So, octal to binary. We start with the number 25, and hopefully you can recall that any 3 binary digits will make up just one of these digits. So what we need to do is break these up into our groups of 3. So dealing with our 1, 2, 4, 1, 2, 4. If we had more digits, we'd have to add another block of 3, 1, 2, 4, and so on. In this case, we've got the number 5, so we need to figure out, well, what do I need to make the number 5? I'll need a 4 and I'll need a 1. That will give me the number 5. So I need a 4, a 1, and don't need any of them. To make the number 2, I don't need any of them. I need one of them, and I don't need any of them. That gives me the number 2. So 010101 is in binary is 25 in octal. Of course, it doesn't matter how many zeros we add here. It's not going to change the number at all because these are our, I can't think of the words. I haven't really used the terms most significant digits yet, but basically if we've got none of these, then we're just adding none of them, none of them, none of them, none of them to our number. Doesn't change the number whatsoever. Alright, so there's that. Let's do hexadecimal to decimal. So in this case, we're starting with the number 1, 5 in hex, or hexadecimal, to go to decimal, just as we did for binary to decimal, just as we did for octal to decimal. We need to figure out the weighting of each column. We do that by getting the base number above each of our digits. So if there was 10 digits, we'd have 16, 16, 16, 16 above every single digit. We start from the right, raise it to the power of 0, and we go across just incrementing by 1. If we had a third digit, it would be 16 to the power of 2. Then a fourth would be 16 to the power of 3, and so forth. 16 to the power of 0 is simply 1. 16 to the power of 1 is 16. If we had a third digit, it would be 16 to the power of 2, which would be 256, and we just keep going up and up from there. Okay, so what we're saying here is we've got one of those, and we've got 5 of them. So we've got 1 of the 16 column, and we've got 5 of the ones column, which is 16 plus 5, which equals 21. So to get from hexadecimal to decimal, we just use our weighting system, just as we did as octal to decimal, and just as we did for binary to decimal. Okie dokie. Last one to do, and then I'm done for tonight, is hexadecimal to binary. To do this, just write this up first. We write down our hexadecimal number, and you may recall, hopefully, in our last video, that any 4 binary digits, any combination of 4 digits, will equal 1 hexadecimal digit. So, we split it up, and this has to become one block of 4 digits, this has to become one block of 4 digits. So we've got 1, 2, 4, 8, 1, 2, 4, 8. So to make the number 5, we're going to need a 4 and a 1. So none of that, one of them, none of them, one of them. So 4 plus 1 gives us 5. Over here, to make the number 1, all we need is one of them. None of them, none of them, and none of them. That gives us the number 1. Again, it doesn't matter how many zeros we place over to the left-hand side, the number still doesn't change. Just as if we had like $5,723, it doesn't matter if we just kept putting zeros there. It doesn't change the fact that it's still just $5,723. So realistically, let's just get rid of them, and we get 10101, which is what we started with up here. Alright, well I think I'm done for tonight. We kind of went through a few things, which was pretty cool. I started off telling you about what we did in the last video. So again, if you haven't looked at that one, go back, go check it out. I then described a few uses where it's cool to maybe use binary, where it might be good to use hexadecimal. I then went on to talk about how our calculator in a very basic way functions. Basically it uses decimal for our input and for our output, but the internal workings are actually done in binary because it's very easy to construct circuits that just have transistors switching on and off. So the calculator has to do the conversion for us, but it just makes our life all the more easier. Okay, then we went on to talk about, well, how can we convert from decimal to octal, or octal to decimal, hexadecimal to binary, and so forth? Because it's very handy to be able to convert between all of these different number systems, because they all could be used in the field of digital electronics. Alright then, thank you very much for watching. I hope you got a lot out of this. If you didn't understand something, be sure to leave me a message, and I'll see what I can do about that. Alright, good night. God bless.